Okay, we need to talk about some new terminology. We are going to learn we are learning for second derivatives. So we have different notation that we've looked at so far. We are watching?
No.
All right, we've got different notation. So obviously these are the original functions. These are the derivatives. They're both the same thing, right? So we write them like this. Does anyone want to guess how I write my second derivative? Yeah, it's just two little things, right? So I put two little things there, and that means second derivative. And d squared y over dx squared. Yep, I know it's a little bit different, but this is the way that we write second derivatives. So if you see these, they obviously mean the same thing, and they follow this pattern. All right, second derivatives are just the derivative of the derivative, right? So it's not something hard. This is something easy that we know how to do. So I'm just going to move this over a little bit. So if I have, let's say that I have 3x squared minus 4 all squared. I want to find the derivative. Who wants to tell me there are two ways I could do this? Give me one. Say it again. Rearrange, someone said. What does that mean? Expand. Okay, let's expand these brackets. So if I expand them, there's two of them and I have to FOIL them. What do I get? 9x to the power of 4. Good. Plus 16. Good. All right, so I would write this out twice and FOIL it. I'm glad that we can all do this in our head now. So if I want to find the derivative, how do I do that? What is it?
48, minus 48.
Good. All right, so that would be the derivative. Is there another way I can derive this?
Yeah.
I can use the chain rule, right? So if I wanted to use the chain rule, you know what? I should have done that first so that they're under each other. So if I want to use the chain rule, what would I do? Yep. X squared minus 4.
Times that times 6.
Good. Okay, so this is the derivative of the brackets. So that means the whole thing is 12x and then 3x squared minus 4. All right, and then the derivative of this is... Whoops, what's the derivative of this? 36x cubed minus 48x. See how if I expand these brackets, that's what I get? No, 36x cubed minus 48x. So yeah, because this is an x times a squared. So it doesn't matter which way you do it. You get the same answer each way, okay? I don't mind which method you pick. They're totally the same. All right, so now that I have this, what is my second derivative?
It's 36 times 3.
Which is?
90, wait,
108. Keep going. X squared.
Minus 48.
Good. All right, that's my second derivative. Okay, let's look at something slightly more complicated and then we'll use it and we'll find some more stuff from it. Okay, let's get rid of that. All right, first, yeah, I'm going to do this one. All right, so if I have y equals 5 over 2x minus 3 cubed. Okay, if I want to find my second derivative, first of all, can I just go straight from there or do I need to do something first? What am I going to do?
You bring that up.
Okay, so what do I get?
2x minus 3 to the power.
Good, does not look like a 3. So I make the power negative, so it's all together. So my derivative is negative 15. Right, times by 2, because 2 is the derivative of the brackets. So I end up with negative 30 over 2x minus 3 to the power of 4. You with me? Now, if I want to find my second derivative, should I have put it in this form? No, because if I put it in that form, I'm going to have trouble deriving it. So I'm actually going to leave it as a negative power because my question's not over yet. So this is actually -5. Sorry, 4. Why did I write that? 4. Okay, so let's find our second derivative. What do I get now? Positive 120, because it's -30 times -4. 2x minus 3. -5. Chain rule again. Good. So what happens? 2. Right, now I'm done, so I can make sure everything has a positive power. So I've got 240, because these two are multiplying, and that is all over 2x minus 3, all to the power of 5. All right, now I'm going to use this. Let's do an example where we actually use it. I'm going to give you another equation. And let me show you how it's actually useful. All right, so I am going to, no, I'm going to do this one. All right, y equals x cubed. Actually, I think this is a question from the book that I'm not giving you. Squared minus 15x minus 7. All right, so if this is my original function, I am being asked to find, this is question 8, by the way. No, it's not. Oh, am I about to accidentally do question 8, which I have assigned you? Let's not do that. Is that 8? That's 8.
Yeah.
Okay, let's not do 8. I wanted to do 7 because I did not give you 7.
Use it.
All right.
Use
Joshua.
it.
Right. If you have a look at 7, you'll understand why I didn't give it to you. We're not using that method. Okay, so y equals 2x cubed minus 21x squared plus 60x plus 5. Okay, so what I'm asked to do is find where the values for the derivative and the second derivative are all positive. All right, John, can you put your laptop away, please? All right, so what I'm going to do is I'm going to find both of those, and then I'm going to say, when are they positive? And remember, when I say is the derivative positive, what's the derivative measuring? The gradient. So what I'm doing is finding the values at which this graph has a positive gradient. So if I find my derivative, what do I get? 6x squared is 42x plus 60. All right, I am going to solve this as a quadratic. So I am being asked, this question asks, when are the values positive or negative? Okay, so I'm going to find out where they're positive. So I want these to be greater than 0. So how would I solve this? Quadratic formula, I don't want to do that. What else can I do? I'm going to factorize. What do I take out as a common factor? 6. Don't. Oh, why is there a 7 in this question? I hate you all. All right, so what is this as a factorized form?
6 and 7.
Stop it. Okay, -2 and -5, they multiply to positive 10, add to -7. So x is 2 and 5. Now, what you need to do here is do some picturing of the graph. Is this what type of graph does this look like? Positive what? Okay, this is a positive quadratic. So I'm just going to, it's a smiley face. If this is 2 and 5, this is a smiley face graph, okay? I am interested in when these values are greater than 0, right? I want these values to be positive. Remember, this is a graph of the derivative, not the original function. So this graph is the graph of the gradient. When these values are positive, the gradient is positive, right? I'm going to show you on Desmos what that looks like in a second. So that means when x is less than 2, right, because that's what this bit is, and when x is greater than 5, the gradient is positive. Does that make sense? Sorry? Okay, what I'm going to do is go over to, oh, crud. Oh, no, there it is. All right, it was this one. Can you see these two values? That is 2 and that is 5. So see what's oh no, this is 2 and, yeah, this is 2 and 5. So when x is less than 2, see how the gradient is positive? And when x is greater than 5, the gradient is positive. When x is between 2 and 5, the gradient is negative. It's going back down, right? So when we go back over here, let me just open it back up again. When we're looking at this section of the graph, when x is between 2 and 5, the values are negative. The values on the other side are positive. So the gradient is positive in these values of x in the original function, and between these values of x in the original function, the gradient is negative. Okay, so then what we can also do is, we're not using second derivatives very much yet. We will do that in the next topic. But what they're going to ask us to do is maybe have a look at when the second derivative is positive or negative. So again, I'm going to derive this. So let's go back up there and find our second derivative. What do I get?
Well,
12x minus 42. So if I'm being asked when this is positive, I want to know when this is greater than 0. So that means 42 is greater than 12x. And that is going to give me the answer of 7/2 is x. Okay, now, if they are now asking me, which they will do for question 8, I think. Yeah. So for question 8, they're asking you when both of those values are positive. I am being told that x must be greater than 3.5. I'm also told that x must be less than 2 or greater than 5. Now, some of these contradict each other, right? This value contradicts that, so I can't use it, right? Because both of these things have to be true at the same time. That's what they're asking. When are they both positive? So do I use both of these or just one of them?
one.
Which one?
Yeah.
The one that works, very helpful. The higher one, because if x is always greater than 5, in this case, x is not necessarily greater than 5. So this is limiting. It gets to be correct at some point, but it starts off being wrong. So this is actually my final answer. When both of them are positive, this is my restriction because it fits all possible criteria. Does that make sense? Glad we're excited about that. Why can't what?
Why do we cancel out the x is smaller than 2? What if the other one allowed?
So you just, if they, well, because
Like, they
one,
contradict, but why did you cancel out that one, not that one?
because this can never be true for that.
But that can never be true for that, so then that one could be wrong.
No, but both of these can be true at the same time. This makes that one invalid, right?
Yeah.
Does it make sense?